All right, let's talk about 6.3, which is about composition of functions. So let's say that f and g are functions. The composition of g and f is denoted this way, with a little open circle between the g and the f. We read this g of f, or g composed with f, right? But g of f. So I would read this g of f of x, and this I would read the same way. This is g of f of x, right? But that's what the composition means. It means that we're going to plug f of x into g. Okay? Let me give you some examples. So let's say that f is 2 minus x and that g is 2x squared minus 3x plus 1. Let's find g of f of x. So g of f of x, right? This is g of f of x. So it means that f of x is 2 minus x, right? So this is g of 2 minus x. So this means that I'm going to look at the function g, and everywhere I see an x, I'm going to replace it with a 2 minus x, right? So this is 2 times x, which I'm replacing with 2 minus x, squared, minus 3 times x plus 1. All right. So that's 2 times 4 minus 4x plus x squared minus 6 plus 3x plus 1. That's 8 minus 8x plus 2x squared minus 6 plus 3x plus 1. And combining my like terms, I get 2x squared. 3x minus 8x is negative 5x. And then I have 8 minus 6 is 2, plus 1 is 3. Okay? So there's g of f of x. Let's find f of g of x, right? F of g of x would be f of g of x. G of x is 2x squared minus 3x plus 1. So this is going to be, I'm going to look at f of x, and everywhere I see an x, I'm going to replace it with 2x squared minus 3x plus 1. So it's going to be 2 minus x. Okay? So that's 2 minus 2x squared plus 3x minus 1. So that's a negative 2x squared plus 3x plus 1. One thing that you'll notice is that the order of compositions makes a big difference in the way the function ends up looking. So g of f is not the same thing as f of g. Of course, we can also compose a function with itself. So we can do f of x, right? Remember that f of x is 2 minus x. So we're going to do f of 2 minus x. That means we're going to look at the function f of x, and everywhere we see an x, we're going to replace it with 2 minus x. So this is sort of like the movie Inception, right? It's a function within a function. So we're going to do 2 minus x. Okay? So there's f of x. 2 minus 2 is 0. Negative x. A negative times a negative is going to be a positive x. So this is just x. So that's kind of an interesting thing. Let's talk about the domain of composite functions, because this is something that's a little bit tricky. But in order to evaluate g of f of x itself needs to be a value in the domain of g. In other words, f of x needs to be in the domain of g, right? Therefore, the domain of g of f is going to be the set of all real numbers in the domain of f, where f of x is in the domain of g. Let me give you an example of this, right? So let's say that f of x is x squared and that g of x is 1 over x minus 4. And let's say that we want to find the domain of g of f. Okay, so first of all, the domain of g is everything except for positive 4, right? Positive 4 will make the denominator 0. So it's all of the real numbers except for 4. So therefore, to evaluate g of f of x, we have to make sure that f of x is not equal to 4, right? Now, if f of x is not equal to 4, then that means that, right, f of x was x squared. So that means that x squared cannot be 4, which means that x cannot be plus or minus 2. Therefore, the domain of g of f is all real numbers except for 2 and negative 2. Okay. Well, note that in the previous example, if I had just found the composite function g of f of x, right, it would have been g of x squared. G of x is 1 over x minus 4, so g of x squared is 1 over x squared minus 4, right? And now, if I wanted to find the domain of this function, I would just say, well, x squared minus 4 is not allowed to be 0, right? And if I solve that, then I see that x cannot be plus or minus 2. And so again, we would get that same answer, right? The domain of, not f of g, the domain of g of f is r minus negative 2 and 2. This doesn't always work, though. So let me give you an example where this doesn't work out. Okay? So let's say that we want to, that f of x is square root of x minus 8 and that g of x is x squared. And let's say that we want to find the domain of g of f. If we try to find the domain of g of f by actually finding the composition first and then figuring out what the domain of the composite function is, we're going to run into the following issue, right? So we find the composition, g of f of x, that would be g of square root of x minus 8, because f of x is square root of x minus 8. G of x is x squared, so we're just going to take x and replace it with square root of x minus 8, and then square that, and we get x minus 8. Looking at this, you may think there's no domain restriction, right? Because x minus 8 is just a straight line. There are no domain restrictions there. But a careful examination of the composition reveals that since f of x is undefined, since f of x is undefined for x, we would need x minus 8 to be bigger than or equal to 0, right? So we would need x to be bigger than or equal to 8, right? So since f of x is undefined for x greater than or equal to 8, g of f of x cannot be defined for x sorry, we're looking for where this is undefined. It's undefined if x is less than 8. Right? It's defined if x is greater than or equal to 8, but it's undefined if x is less than 8. So since f of x is undefined for x less than 8, g of f of x cannot be defined for x less than 8 either. So while it is true that g of f of x is x minus 8, just a linear function, the domain is not all reals, though. Right? It has domain 8 to infinity. Not negative infinity to infinity. If your head is spinning by this point, that's understandable. This is a little bit complicated. It might do you well to go back through and reread this or rewatch this portion of the lecture, or maybe read through it and try to make sense of it on your own. And if you still can't, then rewatch this portion of the lecture. But here's a summary. This is how we're going to go about finding the domain of a composite function. So we are going to start off by just finding the composite function itself and determining what the standard domain of that composite function is. But then we're also going to find the domain of the inner function. And by the inner function, I mean the function that we plug into the other one. So in the case of g of f, the inner function is f. In the case of f of g, the inner function would be g. Okay? But we find the standard domain of the composite function, and then we determine the domain of the inner function. The domain of g of f is going to be the intersection of those two domains, right, from steps 1 and 2. So I'm going to walk you through several examples of this to hopefully make it as clear as possible. Excuse me. So let's say that f of x is square root x minus 1 and g of x is square root 4 minus x. Let's find f of g and state its domain. Okay, so step 1, we'll find f of g. That's going to be f of g of x That's f of square root of 4 minus x. Now f is the square root of x minus 1, so I'm going to write f, but everywhere I see an x, I'm going to replace it with square root 4 minus x. So this is going to be the square root of 4 minus x minus 1. Okay, there's f of g of x. There's not really much simplifying you can do to this, so we would just leave it this way. But if we wanted to find the domain of this, the standard domain of this thing, well, there are two things that need to happen. First of all, 4 minus x needs to be bigger than or equal to 0. And then second of all, the square root of 4 minus x minus 1 needs to be bigger than or equal to 0, right? Because they're both inside of some radicals. So we need two things. We need 4 minus x to be bigger than or equal to 0. And we need square root of 4 minus x minus 1 to be bigger than or equal to 0. So this means that we need x to be less than or equal to 4. This one means, well, it means square root 4 minus x has to be greater than or equal to 1. So so 4 minus x needs to be bigger than or equal to 1, right? If you square both sides. And that means negative x needs to be bigger than or equal to negative 3. So x needs to be less than or equal to positive 3. Okay, so x needs to be less than or equal to 4, and x needs to be less than or equal to 3. Well, so taken together, this just means that x needs to be less than or equal to 3, right? Very good. So then step 2 is to find the domain of the inner function. In this case, the inner function is g. Right? So the domain of g is, well, for g of x, we need 4 minus x to be bigger than or equal to 0. That means we need for x to be less than or equal to 4, just like we saw earlier. So the domain of g is negative infinity to 4. Right? So now step 3 is we take the intersection of these two sets. So in this case, we don't get anything new, because x less than or equal to 4 was already a restriction that we saw in step 1. So it's not, we don't get any new restrictions here. So our domain is still just going to be x less than or equal to 3. So we would say domain of f of g. Maybe I need some notation. So from step 1, I'm going to call this the domain. It's not really the domain of f of g. Maybe I'll call it the domain of f of g star, right? Equals negative infinity to 3. So the domain of f of g is going to be the domain of f of g star intersect with the domain of the inner function g. Right? So that's going to be negative infinity to 3 intersect negative infinity to 4. Okay, sorry. Then the intersection of these two sets is negative infinity to 3. So that's the domain of f of g. Okay, so these are the steps we take. In this case, like I said, the domain that we got at the end of step 1 turned out to be the same as the domain of f of g. But that's not always the case. It doesn't always work out like that. Let me show you some other examples. Okay. So for this one, we just have f of x equals 1 over x minus 1. We want to find f of f and then state its domain. So let's do it. So f of x is going to be f of x. That's f of 1 over x minus 1. So I'm going to look at f, and everywhere I see f, I'm going to replace it with 1 over x minus, everywhere I see an x, I'm going to replace it with 1 over x minus 1. So I'm going to get 1 over x minus 1. Okay, so it's kind of trippy when you are plugging a function into itself. Anyway, this is a complex fraction, so I'm going to multiply by the LCD, which in this case is x minus 1. In order to clear that complex fraction, we get x minus 1 over, if I distribute here, the x minus 1s will cancel and leave 1. If I distribute here, I get x minus 1. So this is x minus 1 over 1 minus negative 1 is 1 plus 1, so that's 2. So it's x minus 1 over 2 minus x. Okay, so there's f of f. Now if I want the domain, I'm going to call this the domain of f star. So the thing that I'm finding, the domain that I'm finding at the end of step 1 is like, it's the standard domain of this function that you get, but that's not necessarily the same thing as maybe a better notation would be to say it's domain star of f. Okay, so it's the domain star of f. So to find the domain star of f, we're going to do, we need for 2 minus x to not be 0, which means x can't be 2, right? So it's going to be all of the real numbers except for 2. Okay, so that's step 1. Now step 2, I need to find the domain of the inner function. In this case, the inner function is f. Right, the domain of f. For f, x is not allowed to be 1, right? Because that would make the denominator 0. So the domain of f is all reals except for 1. So then step 3, the domain of f is the domain star of f intersect with the domain of f. In other words, it's step 1 intersect step 2, right? So it's r minus 2 intersect r minus 3. So remember, in order for a number to be in the intersection, it has to be in both sets. 2 is not in this set, so it can't be in the intersection. 3 is not in this set, so it can't be in the intersection. But every other real number is in the intersection. So the domain of f is going to be r minus 2 and 3. So this time you'll notice that you do end up with a different domain, right? You do end up with a different domain than what you got at the end of step 1. And that's why am I saying 2 and 3? Domain of f was 1. So that should be 2 and 1. My apologies. It should be 2 and 1. So this is the actual real domain of f. This is like the fake domain of f, right? What you get at the end of step 1 is the fake domain. The real domain is sometimes a little different because you have to take the inner function's domain into account as well, right? And so we see that here. So in example 2, these functions or these domains weren't any different from one another, but in example 3 they were, right? Let me take you through a couple more examples. I think the more examples we do, the clearer it becomes. So for example 4, we've got log base 3 of x plus 1 is f of x, and g of x is 2 over x minus 3. So let's find g of f and state its domain. Okay, so first of all, g of f, that's g of f of x. So that's g of log base 3 of x plus 1. So I'm going to look at g, and everywhere I see an x, I'm going to replace it with log base 3 of x plus 1. So I'm going to get 2 over log base 3 of x plus 1 minus 3. And that's about as simplified as that's going to get, right? So there is g of f. But now I need to find the domain of g of f. So in order to do that, I'm going to find I'm going to find the domain of g of f star, or the domain star of g of f is what I've been calling it. So here's what can go wrong with this function. So first of all, for a logarithmic function, we need the argument to be strictly positive, right? So we need x plus 1 to be strictly positive. And then for a rational function, we need the denominator to not be 0. So we need log base 3 of x plus 1 minus 3 to not equal 0. So if we solve both of these things, we get x has to be bigger than negative 1, and log base 3 of x plus 1 cannot equal 3. If you exponentiate by 3, then this means that x plus 1 cannot equal 27, right? 3 cubed is 27, which means that x cannot equal 26. Okay, so x has to be greater than 1, and x cannot equal 26. So that means the domain star of g of f is negative 1 to infinity except for 26, right? Negative 1 to infinity except for 26. Okay, so that's step 1. Now step 2, we need to figure out the domain of the inner function. The inner function in this case was f of x. So for f of x, we just need x plus 1. We just need x plus 1 to be greater than 0, which implies that x needs to be greater than negative 1. So the domain of f is negative 1 to infinity. That means that the domain of g of f is going to be the domain star of g of f intersect domain of f. So that's going to be domain star of g of f was negative 1 to infinity minus 26. Right? So it's that intersected with negative 1 to infinity. Well, so that intersection is just going to be negative 1 to infinity minus 26, right? Because 26 can't be in the intersection because 26 isn't in this first set. But every other number in this interval is in this set. So this is just negative 1 to infinity minus 26. Okay, so this is another example of one where the actual domain of g of f was the same thing as the domain star of g of f. But again, that it doesn't always work out that way. One more example of this. So we have f of x equals e to the 2x minus 3 plus 4, and g of x is ln of x minus 4 plus 3 over 2. Find f of g and state its domain. Okay, f of g of x. That's going to be f of g of x, ln x minus 4 plus 3 over 2. What does that mean? It means I'm going to look at the function f, and everywhere I see an x, I'm going to replace it with ln of x minus 4 plus 3 over 2. Woo! So I'm going to say this is e to the power of 2 times ln of x minus 4 plus 3 over 2 minus 3 plus 4. That's ridiculous, right? I'm using a little caret symbol because this would be too much to write in just a single exponent. So I'm using the caret symbol here. But what do we get? Well, this 2 cancels that 2. So I get e to the power of ln of x minus 4 plus 3 minus 3 plus 4. Ridiculous, right? But anyway, this 3 and that 3 cancel. So this gives me e to the ln of x minus 4 plus 4. The e and the natural log cancel. This is just x minus 4 plus 4. Oh, and the 4 cancel. Oh my goodness, this is just x. This is just x. Okay. So f of g of x is just x, right? But now if you look at the domain, right? So the domain star of f of g of x would be all real numbers, right? Because the domain of just f of x equals x is all reals, right? So the domain star of f of g is all real numbers. But let's see what the domain of the inner function is. So the inner function was g of x, right? For g of x, we have a logarithm up here, and the argument of our logarithm is it needs to be strictly positive. So we need x minus 4 to be greater than 0. Which means we need x to be greater than 4. So the domain of our inner function g is 4 to infinity. So now step 3, the true domain of f of g is the fake domain of f of g intersected with the domain of g. Okay, well the fake domain of f of g was all real numbers. The domain of g was 4 to infinity. So the real domain of f of g is all real numbers intersect 4 to infinity. That's just going to be 4 to infinity. 4 to infinity. So you can see that the domain you got, the fake domain you got in step 1 is not the same thing as the real domain that you got in step 3. Okay, so sometimes the fake domain is the same thing as the real domain, right? Sometimes it's not, right? So what you do to find the domain is find the fake domain, then find the domain of the inner function, then take the intersection of the fake domain with the domain of the inner function, and that's going to be the true domain. Okay? So that's that. So another interesting thing to point out is that the domain of this function is 4 to infinity. So what we're saying is that when you compose f and g, you just get x back out, but it's not x on the entire real number line. Like if you were looking at a graph of this function, it would look like this straight line, right? It would sort of look like this straight line f of x equals x, except that it wouldn't include any of this stuff down here. It would start at x equals 4 and shoot off that way. So really this function would only look like this portion of the graph. The rest of it would not be on there, right? So it would look like, instead of looking like a line, it's just going to look like a ray. Anyway, so that's kind of interesting, I think. Okay, so that's how compositions work. Now I'm going to take a little detour and remind us a little bit about the derivative. It's been a while since we've calculated any derivatives, so let's remind ourselves how derivatives work. One of the reasons that I want to do this is just to point out that when you're doing the derivative, it's very similar to doing a composition, right? When you're trying to find f of x plus h, that means you're going to look at f, and everywhere you see an x, you're going to replace it with x plus h, right? So so it's kind of it's pretty similar. So let's calculate the derivative of this function here, 3x squared plus 2x. Okay, so f prime of x, the derivative is going to be the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so that's the limit as h approaches 0. I'm going to look at f of x, and everywhere I see an x, I'm going to replace it with x plus h. So this is going to be 3 times x plus h squared plus 2 times x plus h. So there's f of x plus h. Then I need to subtract off f of x, and then I need to divide by h. So let's expand. We've got 3 times x squared plus 2hx plus h squared plus 2x plus 2h minus 3x squared minus 2x all over h. Remember, our goal is we want to be able to plug in 0 for h. The problem is if we do that right now, we're going to get a 0 in the denominator and it's going to be undefined. So we need to cancel this h off in the denominator somehow. I think we'll be able to do that once we cancel some things. So we've got limit as h approaches 0 of 3x squared plus 6hx plus 3h squared plus 2x plus 2h minus 3x squared minus 2x all over h. And now we get to cancel a bunch of stuff. The 3 terms we have left over all have an h in them, so I'm going to factor out that h. That allows me to cancel the h in the denominator, which is what I wanted to do, right? Now I can go ahead and plug in 0 for h, and I'm just going to get 6x plus 2. There's the derivative. All right, so we've done derivatives. We were doing derivatives earlier on in the course, right? So we've done a bunch of these things by now. So, but there were 2 reasons that I wanted to bring up derivatives again. First of all, because I think it's going to be good for you to practice this before you head into calculus. But the 2 reasons were, first of all, to point off that this is really a composition of f and x plus h, right? So when you're doing derivatives, you're really doing some kind of like composite function. But the other reason I wanted to point it out is because if you take the derivative of a composite function, it turns out, this is really nice. If you can think of a function as the composition of 2 easier functions, then you can find the derivative of the composite function by finding the derivatives of the individual ones. In other words, h prime of x is just f prime of g of x times g prime of x. So it's the derivative of the outer function, well, it's the derivative of the composition multiplied by the derivative of the inner function. Now, we're not going to practice applying the chain rule in this class. That's a calculus topic. So you're going to do that in calculus, right? You're going to do the chain rule so many times in calculus, right? So I'm not going to practice, we're not going to practice applying the chain rule in this class, but what I do want to practice is trying to think of functions as compositions of simpler functions, okay? So for example, let's see if we can rewrite each of these functions in terms of these simpler functions, p, q, and s. Okay? So if we have f of x equals ln of x squared, we need to get really good at thinking about this as a composition of 2 functions, or 3 functions potentially. So to do that, I kind of think what I see here basically is a natural log function. We're taking the natural log of something. Now we're not taking the natural log of x though, we're taking the natural log of x squared. So really we're taking the natural log of x squared. We're taking the natural log of p of x. So this is really natural log of p of x. Well, what's the natural log function? In this case we called the natural log function q. So this is really q of p of x. In other words, f of x is really q, it's really q of p. You could leave it this way. I mean, I'm fine with that. But I'm just saying, it's the composition of Q and P, right? That's what f of x is. It's the composition of Q and P. Okay, let's do part B. We have f of x equals square root of ln of x. This time ln of x is the inner function. We're taking the square root of ln of x. So we're taking the square root of q of x. Right? So this is the square root of q of x. Right? Well, what's the square root function? In this case, we called the square root function s. So this is really s of q of x. Right? It's s of q. S of q of x. Let's do one more. So in part C, we have f of x equals ln of square root of x all squared. Okay, so I think the outermost function is we're squaring something. Now, what are we squaring? We're squaring the natural log of something. Okay, what are we taking the natural log of? The square root of x. So the innermost function is the square root of x. And so, in other words, this is natural log of square root of x. That's s squared. The natural log function is q of x. So this is really q of s of x squared. Well, what's the quadratic function? We're calling that p of x here. So this is p of q of s of x. 3 sets of parentheses, right? In other words, it's p of q of s of x. All right? So this is the kind of thing that we need to get really good at doing in order to be prepared to apply something like the chain rule in calculus. So you're going to have several examples in the or several exercises in the homework that ask you to rewrite a function as a composition of two simpler functions. Now, while we're on the topic of the chain rule, as I said, we're not going to practice applying the chain rule in this class, but what I do want to practice is simplifying what you get after you apply the chain rule, because this is another thing that kind of can trip students up. Okay, so each of these functions are the functions from the previous page. And if you apply the chain rule to find their derivatives, this is what you get as the result. So for part A, f prime of x is 1 over x squared times 2x. Let's see if we can simplify that. So I'm not asking you to do any calculus, I'm just asking you to do the algebra to simplify this expression. 1 over x squared times 2x. This one isn't terrible. I think the x will cancel one of those x's and leave a 2 over x as your final answer. So there's f prime of x. Let's do part B. So again, if you apply the chain rule to this function, this is the nastiness that you're going to end up with. Let's see if we can simplify it. So we have 1/2 times ln of x to the negative 1/2 times 1 over x. What in the world is going on? Well, ln of x to the negative 1/2, that would be the same thing as 1 over ln of x to the positive 1/2. You can rewrite that as a square root if you want. So I'm going to rewrite this as 1 over 2x, right? I'm bringing this x over. 2x times the square root of ln of x. Okay? And then let's do that last one. So this was part C in example 7. And this is the derivative that you get after you apply that chain rule. Let's see if we can simplify the derivative. Okay, so I'm going to have 2 times ln square root of x times 1 over square root of x times 1/2 x to the negative 1/2. I'm going to rewrite all of these individual factors as fractions. 2 over 1, ln root x over 1, 1 over root x, 1 over 2. And then x to the negative 1/2 is the same as 1 over x to the positive 1/2. A few things cancel, right? The 2 there and the 2 there cancel. This square root of x and that square root of x do not cancel. Don't try to cancel them because you're taking natural log of this square root of x. It's not like natural log times square root of x or something. So they don't cancel. Those don't cancel. But notice that x to the 1/2 is the same thing as the square root of x. And square root of x times square root of x is just going to be x. So putting this all together, in the numerator, all we're going to have left is ln of square root of x. And then in the denominator, all we're going to have left is x. So that's much cleaner than the craziness that we started with, right? So you'll have some exercises in the homework that ask you to simplify derivatives. You're not finding the derivatives, you're just simplifying the derivatives. And again, this is to help you so that you're really comfortable with the kind of algebra that you're going to have to be doing in calculus all the time. Okay, so that's that. We'll see you in the next section.